In this video, we'll be talking about hemostasis and coagulation. As you know, all implanted materials have to contend with our body's responses to injury. So with this in mind, we're going to be talking about blood contacting devices and the hemostatic mechanisms that they have to contend with. So specifically, we'll be covering platelet binding and activation and the coagulation cascade. So after an injury, hemostatic mechanisms serve the purpose of stopping bleeding. And this is accomplished three ways. First is vascular constriction, but then our focus is going to be on these two bolded ones, the formation of a platelet plug, and then blood coagulation, also known as thrombosis. So the two elements with platelets we'll be talking about are first, they initially reduce bleeding through the creation of a platelet plug, and then they further stabilize that plug through activation of the coagulation cascade. So platelets really have a key role in hemostasis. So what are platelets? Well, I'm not going to show this video, but it's a very nice video that talks about platelets and shows a little bit about the process of platelet formation from megakaryocytes. If you're interested, follow the link and you can check it out on YouTube. So platelets, they're very small. They're about 3 to 4 microns in size, and they're irregularly shaped. But a key point is that they're actually cell fragments. So they have no nucleus, but they do have some organelles. So they have an endoplasmic reticulum and a Golgi apparatus. So basically, as you'll see if you watch that video, platelets are pinched off pieces of megakaryocytes. But because they're just fragments of cells, they can't proliferate and they have a very short lifespan of only 5 to 9 days. Platelets do contain a multitude of cytokines, growth factors, and proteins that are all related to hemostasis. And these are packaged within the platelets into these vesicles known as granules. And there are several types of granules. They're often labeled with Greek letters. So you have alpha, delta, lambda, etc. So the contents of these granules are very important. So the alpha granules, they contain fibrinogen, factor 5, factor 13, among other things. So everything in red on this slide is pertinent to the coagulation cascade. The dense granules, so the delta granules, they contain adenosine diphosphate or ADP and calcium ions, among other things. And an important point here is that ADP activates platelets. So granule contents are released when platelets are activated. So here you can see there's a little bit of a positive feedback loop because when they become activated, they release the ADP and other things that activate more platelets. So unactivated platelets, which are shown down here, they have a disc-like morphology, but once a platelet becomes activated, the platelet is going to swell a little bit, and then it takes on this really irregular shape, and it contracts its cytoskeleton. So this over here, these are showing what an activated platelet looks like. So when they contract, that's when you get the release of the granules. Okay, so how do platelets adhere and form a platelet plug and become activated? Well, this happens via several ways. First is that the damage to the endothelium that occurs during an injury is going to expose some underlying extracellular matrix proteins. So those are proteins from the subendothelium or below the endothelial cells. These include collagen and fibronectin, and then there's also this von Willebrand factor, which can stick to the collagen. So there's some von Willebrand factor that will just circulate in the blood. And so platelets, they will adhere to these proteins that are exposed on the subendothelium, or if we're thinking about biomaterials, if these proteins adsorb onto the biomaterial surface. And so this mechanism of adhesion is very much like cell attachment. So if you recall, as we said a couple slides back, platelets are just cell fragments. So they also have integrins on their surface. And they have integrins that recognize these proteins. So they have these integrin receptors that can bind collagen and von Willebrand factor. I made those two in red above because those are potent platelet activators. So once a platelet adheres to these, that's going to trigger degranulation of the platelet. And then that degranulation triggers more platelet activation because the platelets release large amounts of that adenosine diphosphate and calcium ions. They also release thrombin and thromboxane. So all these things activate more platelets and promote platelet adhesion. So this is just showing a little bit more about the mechanism of adhesion. So here you see collagen exposed from the subendothelium. Von Willebrand factor can bind to that collagen, and then the platelets have a receptor, an integrin. So this GP, so that's a glycoprotein 1b95 that binds to von Willebrand factor. They also have this other integrin, GP2b3A, that binds to fibrinogen. And here, what you see is that one molecule of fibrinogen can bind to two platelets. So that's going to facilitate the aggregation of platelets and the formation of a platelet plug. But that platelet plug on its own is not going to be very strong. So if there's any pressure applied, it's going to be easy to open that hole back up if it's just a platelet plug. So we need further stabilization, and that's achieved through the coagulation cascade. Specifically, it's achieved by platelets promoting localized blood coagulation. And that localized coagulation results in the maturation of the thrombus. And the key thing that we get to is that there is a meshwork of fibrin that encases the platelets. And in this case, the fibrin, it acts to bridge plasma proteins in the platelet interior, and then it prevents further bleeding. So you can think about it as reinforcing that platelet plug. So how does the fibrin mesh form? Well, this is a cartoon illustration from your textbook that shows kind of this process. It is self-assembly of fibrin fibrils, but fibrin doesn't just naturally self-assemble because it exists not as fibrin, but as fibrinogen, which is also referred to as factor 1. And then fibrinogen is cleaved by an enzyme known as thrombin, and then it produces a fibrin dimer that then self-assembles. So that's where the coagulation cascade culminates, in this conversion of fibrinogen to fibrin. But how do we get there? So the coagulation cascade, it's a very long stepwise process, and we'll go through it, but it kind of culminates in this common pathway. So that's where the fibrinogen conversion to fibrin occurs. So this key step here is thrombin cleavage, as I mentioned, of fibrinogen already, which polymerizes there. So your book talks about, I think it approaches it from the other angle where you have the extrinsic and intrinsic pathways, and we'll talk about that as well, but both of them converge in the common pathway. So we're going to think about this kind of backwards. So fibrin's what we want. How do we get there? And your book also has this nice table that shows some of the clotting factors here. As I said on a slide earlier, factor 1 is fibrinogen, etc. And then factor 13 is an important one. So that's another enzyme that stabilizes fibrin. So it kind of cross-links the fibrin fibers. But what about this common pathway? How do we get there? So the common pathway kind of picks up when you have attached to the platelet membrane this factor 5. So we already have a platelet plug. Factor 5 attaches to the platelet membrane, and factor 5 is a receptor for another factor known as factor 10A. And then these things together, this complex along with calcium ions, is called the prothrombin activator. And what happens there, so that's very important. So this is that complex, the prothrombin activator, that facilitates the conversion of prothrombin to thrombin by factor 10A. And so factor 10A, along with the prothrombin activator complex, converts prothrombin to thrombin, and then now thrombin can convert fibrinogen to fibrin. So that's illustrated here. Thrombin also serves to activate factor V, which, when activated, accelerates the conversion of prothrombin. So it's kind of another positive feedback loop here. Thrombin also activates this factor 13. So it activates factor 13 to factor 13A. Anytime we have an A there, that's the activated factor. And then that covalently cross-links fibrin in the presence of calcium. So we'll see calcium is really important in a lot of these steps, a lot of these reactions. So that's the common pathway. Now, as I mentioned before, the intrinsic and the extrinsic pathways converge on this common pathway. So down here, this is where the common pathway is. So what are the intrinsic and extrinsic pathways, and how do they work? So first, we're going to focus on the extrinsic. So the extrinsic pathway is also referred to as the tissue factor pathway. So when we have an injury, we know we get release of inflammatory cytokines. And so these cytokines, like interleukin-1 and tumor necrosis factor alpha, they induce release of tissue factor, abbreviated TF, which is released by macrophages and endothelial cells at the site of injury. Tissue factor is important because it binds with factor 7 on the surface of a phospholipid membrane. And wouldn't you know it, we have lots of phospholipid membrane around because we have a platelet plug, and platelets are cellular fragments, so they have that same lipid membrane. So at that point, factor 7 is converted to factor 7A, then tissue factor, the tissue factor 7A complex converts factor 10 to factor 10A, which that, as you recall, that's what we need. Then that will kick off the common pathway. So then that can proceed. We get prothrombin activation to thrombin, then fibrinogen to fibrin, and then the fibrin meshwork. And this can occur very quickly. Clotting can commence within 15 seconds. Now, the intrinsic pathway is a little bit different. So this begins actually with adsorption of factor 12 onto a negatively charged surface. So that right there, you should say, oh, well, if I have a negatively charged biomaterial, that's going to be really bad for a blood contacting device because factor 12 will adsorb and you get coagulation via the intrinsic pathway. But not just with biomaterials, though. This happens in the context of injury as well. So we have glycosylated ECM molecules that can have a negative charge, the anionic, and then also platelets can secrete polyphosphates. So over here, I've got a short video that we'll go over to YouTube on to watch the intrinsic pathway in action. So we're going to skip through most of this because there's a lot of waiting involved, but I'll talk you through and narrate the video. So this is a blood clotting time assay, essentially, being performed. And you can see this person, he's going to prick his finger to get a droplet of blood, which he's then going to put onto this glass slide. And so we won't watch all of that. We'll fast forward. So you see we have a droplet of blood now. And then after it's there, he's going to start probing it with this little lancet. And the video goes on for quite a while. So you can watch like there's nothing happening. It's just a droplet of blood. But once we skip ahead to the end here, so this is after about 2 minutes, still just a droplet of blood. But then now, once coagulation starts to occur, you get the fibrin polymerization. So this right here, this is just a little bit of fibrin mesh that he's actually able to pull up out of it. And he says this is your chlorine time, should be clotting time, of course. All right, so as I said, the intrinsic pathway also known as the coded pathway, starts with adsorption of factor 12, which gets converted to factor 12A, and this happens when you have negatively charged surfaces. Then factor 12A kicks off this cascade, so you get, it leads to factor 9A, shown all the way down here. Again, we see some more calcium is important, but factor 9A and factor 8 form a complex on the surface of platelets. So again, they're reacting sort of on that platelet plug, and then they convert factor 10 to factor 10A, and then now we get the common pathway. Can commence. So via this method, or this pathway, clotting can initiate within just a few minutes. So now here you see the big picture. So the extrinsic and intrinsic pathways are really just different routes of getting to the common pathway to produce fibrin from fibrinogen. So we'll stop here for now, and in the coming videos we will discuss methods for inhibiting coagulation as well as methods to test the hemocompatibility of medical devices.